Hi, in this video we're going to continue looking into this 2-wire RGB LED chain. In the first video we looked at the protocol that's being used to control the chain and identified that there are two sets. There's the odd set and the even set of LEDs. In the second video we had a bit more of an in-depth look into what's going on the wires, and we also built up this very simple control circuitry and connected it to an STM32. In this video I'd like to start with building a very simple bit banging application which will hopefully be able to control these LEDs. In the previous video we never powered the LED chain, so I'd like to do that now quickly just to see what happens. I'm going to use this ST-Link to provide the power, and you can see that the LED has come on the STM32. Nothing in the chain is happening though, which indicates that either they require controls and they start or they power up in the default off state, or perhaps that clock that we were looking at earlier on the scope is missing. Before writing any code, I'm going to hook the scope up so that we can have a good idea of what effect our software is actually having on the wires. The first point is this green wire, which is the supply voltage to the LED chain, and the second point is this black wire, which is the 0 volts or reference point. I'm just going to hook the scope up again so we can see what happens, and as you can see we initially get this 1.85 volts, which is a little over 0.7 volts drop per diode. One of the first things we're going to need is the schematic for the blue pill. The schematic shows us that port C pin 13 is connected to an LED, so we can make use of that for visual feedback. And if you remember from the previous video, we connected the LED chain's transistor to port C pin 9. I've just written out the beginnings of our bitbang code. In Arduino world you have a sort of a setup configuration function followed by a main function which is called over and over again. In the STM32 startup scripts that ST have provided, we have a similar sort of thing. We've got this system init function before libc is started, and then our main function is called. So in the sysinit function we have to configure the pins, and then in the main function we can run our bitbang code. If we have a look at the reference manual for this part, we can see that this is actually a lot more complex than a simple AVR. The Cortex M3, which is the ARM core running our application, is actually quite far removed from the peripherals that we're hoping to use. GPIO-C and GPIO-B, for example, are found on the APB, which is a peripheral bus. What we need to do now is effectively turn the power on to these peripherals that we're hoping to make use of. In the reset and clock control block, we find some registers which have control over the various peripherals. Each bus has its own clock enable register, and as we identified earlier, GPIO-B and GPIO-C are on the peripheral bus 2. So if we have a look at the peripheral bus 2 enable register, we have to set as a 1 in bits 3 and 4 to turn on these GPIO ports. Looking back at our code, you can see that that's happening here. Next, we have to configure the GPIO pins. If we come to chapter 9, we can see the registers related to this. And we have this configuration register which is split across two 32-bit registers. Because we're using pins 9 and 13, that means that we need to use the high register both times. In this register we can see that we have a 2-bit mode and a 2-bit configuration values. We want to output a value, and we're not terribly fussed by speed, so we want to output at 2 MHz. The different values here can control things like drive strength and slew rates. Now that we've configured it for output, we want to configure it for a general purpose push-pull output, and so we need to put a 00 in the configuration bits. Looking back at our code, you can see that we're doing this here. Port B, pin 9, is set for an output mode with a maximum of speed of 2 MHz and with a push-pull. Finally, we set the LED and the chain to a default state, and that makes use of these macros that I've written up here. The active high and active low macro will make use of this BSRR register, and looking at the datasheet we find that this is actually a neat little register which allows us to write a single bit to set or reset the value of a GPIO pin. This prevents us from having to do a read, modify, write or similar action. What you can see is that the low 16 bits will set the relevant pin, while the high 16 bits will reset the relevant pin. Looking at the code, we set a single bit with an offset or shift of the pin's number and then a further 16 steps if it's a disable or a reset action. If we were now to load this onto the STM32, we should see the little green light come on. And there we go. Now that we have basic control over the GPIO pins, we can start to toggle them, which will make the LED flash and will be visible on the scope. I've written a very primitive delay here which will simply use no ops to waste time, and either side we turn the LED on or off. If I write this to the STM32, then we should be able to see things on the scope. As you can see, we've got a current cycle time of about 98 milliseconds or 10 Hz. Reviewing the first video, we can see that the data low period needs to be 1.6 microseconds and the high needs to be between 1 and 3.4 microseconds. Unfortunately, with a bit of maths, we can see that the current configuration is not a viable option for controlling the LED chain. To produce a 1 microsecond pulse, we'd need approximately 0.6 of a NOP. Even if we just use a single NOP in between the operations, we can see that we don't get what we expect. 50 milliseconds divided by 32K is approximately 1.5 microseconds, or around about 333 kilohertz. Looking at the scope, we get about 320 kilohertz, but we get this very asymmetric waveform. Moving the scope probe from the power rail of the LEDs to the signal directly from the STM32, we see more like what we would have expected, which either points out the switching characteristics of the transistor or potentially some capacitance. Given that the LED chain worked correctly with the other controller, I'd suspect that this points more at the switching characteristics of our circuit. Interestingly, I just swapped out the transistor. It was a 2N3906, which was just in a bag of miscellaneous transistors, and I've actually replaced it using a brand new transistor from a fresh bag. As you can see on the scope, it's improved the waveform quite a bit. The orange reference at the top is what we had before, and the live yellow is what we have now. The negative pulse is now about 700 nanoseconds, and I wonder if this is going to be good enough. I've just done a bit of work off camera. I was having some difficulties getting the timing to work out by using just NOPs, and so what I've actually done now is I've taken the system clock and configured it for full 72 MHz, which is what this part is rated for. Clock configuration is a bit complex, so I'm not going to go into it now. But suffice to say, we can now run the core at 72 MHz instead of the previous 8, and we should be able to do a lot better in terms of timing. Because we're running now approximately 9 times faster than we were before, we're going to need a whole load of extra knobs. No operations are really not a nice way to do this, but for sort of a bit banging proof of concept they work okay. What we end up with is this series of definitions making larger and larger and larger chains of NOPs, which in turn incur larger and larger delays. Using loops is a viable option, but it does become a little bit unwieldy with a small number of NOPs, which we do have in a couple of places. Referring back to the previous video, we remember that the zeros are represented by a short low pulse and then a long high pulse, and the ones are represented by a short low pulse and then a short high pulse. To recreate these pulses with their correct timings, we can refer back to the first video again and use these figures that we've kept. To achieve the low pulse, which initiates each bit and should take approximately 1.6 microseconds, we're using the 160 NOP chain. To send the 0 bit, we're using the low pulse, which we've defined above, followed by 185 NOPs to give the high period its duration. A 1 gets the low pulse again, followed by only 20 NOPs. At the end of the packet, it seems to be necessary to set the signal low for a duration, and for that we're using 480 NOPs. We can then start to chain these together. This macro will issue the address value 1, using the 5 bits as discovered in the first video, and this macro will issue the address number 2. We can then bolt the blue, green and red fields onto the end of the address, followed by a chain end operation. I was also playing around with the AC type waveform, which I suspected might be a clock, and it doesn't appear to be necessary at all. Setting the chain's supply voltage to the low point will actually disable the LEDs, and setting it to the high point will enable the LEDs. This allows us to issue a PWM brightness control scheme on top of the colours that we've already assigned to the chain. If we now set some values for the blue, green and red fields, then we should be able to see that take effect on the chain. I'm going to set LEDs with address 1 to green and LEDs with address 2 to red, and then reflash. And there we go. Looking at the scope, we can see that our frames have come through nicely. We can verify our timing characteristics by using the cursors. The low period here is approximately 1.5 microseconds. The long high period is about 3.4, and the short high period is approximately 1 microsecond. If we zoom out further, we can see our 2 frames on the bus and the dead time between the 2 packets that we're sending. If we now enable the blue colour on the LEDs with address 1, then we'll see an interesting effect. Hopefully you can see that the LEDs are actually lit, they're just incredibly dim, and I think this is a side effect of the resistor we're using. Putting 2 47 ohm resistors in parallel here will drop the resistance to 23.5 ohms, and the AE blue LEDs will light up much better. I've now implemented a simple state machine which will pick out which of the colours need to be turned on based on which colour is currently active from the 8 available. Each iteration through the loop will step the colour on by 1 and then transmit the address and the colour for each of the sets of LEDs. Looking at the scope trace while we're running this program, we can see the same step pattern that we saw previously based on which colours are active. In the next video I'll look at using something more suitable like a timer with DMA or perhaps SPI to make these waveforms. The current bitbang implementation is very restricting in terms of what we can do. Any processing that might be required during the packets will immediately push the timing out of spec, and this current implementation is not very flexible in terms of what colour we want to use. I've pushed the sources to GitHub, so feel free to check that out. I'll put a link in the description below, and I'm still interested to know what these LEDs might be, so if you have any ideas, that'd be brilliant. See you next time.